Alright, so combining the terms that we just developed, we can assemble our Reynolds average and Navier-Stokes equations. Or commonly referred to as just the Rand's equations. So we have partial derivative of ui, ensemble average ui with respect to t, plus partial derivative of ui, ensemble average ui, times the ensemble average uj with respect to dxj. It's going to be equal to minus partial derivative of the pressure, ensemble average pressure, dxi, plus 1 over re, the Reynolds number, times the second derivative of the ensemble average of ui with respect to dxj, minus our Reynolds stress term with respect to part derivative dxj, and then we would also have a forcing term if need be from it. We could also write an equivalent equation for a general scalar. So by scalar we mean something like temperature, moisture, humidity, anything like that that we could go through it. For our thermal energy equation from lecture 19, for example, looking at the incompressible version, for temperature we would have that if we take T, our instantaneous temperature, as the ensemble average plus the fluctuation from that, then we would have our equation would just end up being the time rate of change of the ensemble average temperature plus the advection of that temperature by our mean wind equal to our molecular diffusion of the temperature, just our second derivative there through our molecular term, minus, and then here we would get a similar term to our Reynolds stress where we'd have a Reynolds flux term. Sorry, T there. So duj prime times dt dx partial derivative with xj. And these two terms combined, so these two terms both represent what is referred to as the turbulence closure problem we talked about just a second ago. Basically what's happened is if we look at, for example, just the Reynolds stress term, we've added 6 new independent unknowns. To our equation set, where the Reynolds stress tensor, similar to the stress tensor itself, is symmetric tensor for all flows. So what does it mean? Well, we need new equations for the Reynolds stress and the flux if need be. So basically what it says is that, well, we recognize that turbulence has this quantity that basically the statistical quantities seem to be what we can predict in a more meaningful way when we write the equations in that manner. So we break the equations into basically the mean and standard deviation, if you want, so the mean and the fluctuation from the mean. We find out that as we go through that process, we end up with a closure problem of its own, where we now have, and this should be a prime on this T, by the way, where we now have a closure problem of our own, a new closure problem that we've created, which is what we call the turbulence closure problem. Now, we're going to talk more about how we actually do this in practice in the next lecture, but there are two basic approaches. The first one is what's usually referred to as local closures. And local closure models basically assume that our unknown turbulence quantities can be parameterized. So what we're talking about is this would be like, right, u prime I uj prime, right? That's what we mean by our unknown turbulence quantities. These can be parameterized at any point in space as functions of the local values and or gradients of the average. So these can be parameterized as functions of the local mean values or gradients in the flow. So at any point. Basically what they do is they use an analogy to molecular diffusion. And they treat turbulence as a diffusion process itself, just an enhanced diffusion process. The other types of schemes that are common are what are called non-local closures, kind of other class. And these basically assume that unknown quantities can be parameterized as a function of any number of points. In the flow. Many times actually even taking into account basically all points contributing to any given point. So they treat turbulence as a superposition of many eddies of different size that transport quantities, so a scalar value or the velocity field or whatever quantity that of interest, like an advection process. In the end, most RANS modeling actually uses this category, and this is what we'll focus on in future classes. While there are some nice non-local closure models that have been developed, they stay mostly in the purely research area and haven't seen as much general applicability. Although people have used these non-local closure models to basically develop local versions of them, or to help kind of give them a theoretical basis for their local closure models. All right, that ends this lecture.